可以看清楚。
有。
Okay, I will try to take another maybe 40 to 50 minutes to briefly show you the tune mass tempo, and that's something I think we are interested in. And you already see, I think you already see these pictures here. That tune mass tempo. Well, I'm not going to show anymore because I talked about this earlier. This is the really typical example of tune mass tempo. The same thing in this tune mass tempo. And there are a lot of tune mass tempo around in the big cities, so particularly in Japan or in New York. The New York, because of the strong wind, the Japan is the strong wind plus the earthquake. So that's why you already see that, right? Then I'm going to talk about these a few items very briefly, quickly. And if you look at this, it's a dimensionless. That's what I'm going to talk a little bit. When you have tune mass tempo, then you do that. And then we're going to talk about steady state response and the frequency response functions. So when we look at that, all right. And again, you already know this, saw this. And that's really a basic equation for tune mass tempo. And we assume that K1 and M1 are the system or won't damage the structure when the external forces come in. The external forces can be the strong wind, can be earthquake. That's the purpose. So we have this is what the Newton law, the spring force and despot force, and the despot always proportional to the velocities, because anything proportional velocities, they will take out the energy from your external forces. And I didn't prove to you how they do it, but maybe later on I will prove to you why, to talk more about why the spring force or why we need despot. And that's the Newton law, and I think we can just keep going like that. So eventually, that's the equation of motion that we supposed to have. And U1 is our external force. Assume we have only one external force source. And your homework really look like this. Except your external force come from your rough rod, and that rough rod proportional to the shapes of the rod and also the slot, something like those the derivative of the rod shapes. But anyway, that's the typical equations. We have very simple. Now you might ask, can I model a 101 just by a simple mass and simple spring? That's a good question, right? Can I do that? Well, the answer is no. But if you know the dominant frequencies, if you look at in the model coordinates, then that's M1 and K1 can represent your frequencies very well. So don't just say, well, this is too simple, only one mass, one spin. That doesn't look like the 101. No, that's not true. The tune mass tempo, as a matter of fact, you can tune mass tempo, you can tune to only certain number of frequencies. I will show you the frequency response plots, then you was able to see that. So, and then you keep in mind that M1 and K1 will be the system, and all the quantity with subscript 2, that is the tune mass tempos sense. Okay, now we already discussed about the positive definite sense, and so I'm not going to talk more about this. Let us look at dimensionless. All right. And this is defined K1 divided by M1. Let's take a square root of that. That's our radian per second, and that's our frequencies. And omega 1, that's our system frequencies. Omega 2, that's our tune mass tempo frequency. And then we have mu m, that's m2 divided by m1, that's dimensionless. That means your tune mass divided by your system mass. Makes sense, right? And then mu omega is omega 2 divided by omega 1. That makes sense, right? That's also dimensionless. Then I have a rho. That's the damping ratio. That's a dimensionless too. Now the damping ratio from your tune mass tempo. And exactly the same what we talked before. So all this definition are nothing new, just based on whatever we already learned from our single degree of freedom system. All right, let's move forward. So this is 3 dimensionless quantities. To design a device, we need to parameterizations for that. So the whole system, based on that dimensionless quantity, we can rewrite it to become this. That's based on that equations. And that equations. And then we sub all those dimensionless the quantity in there. Then we have omega 2 here, we have the dimensionless mu omega. So because our omega 2 will be our design parameters. So what kind of frequency am I supposed to have for my tune mass tempo? So that is the design parameters. W1 will be our design parameter. W1 is fixed. mu1 is design parameters. So how many design parameters we have? How many? We have so how many we have from here? We have M2, we can change. We have K2, we can change. We have zeta 2, we can change. And so basically we have 3 parameters. So we do have a 3-dimensional parameters really we can use as our design parameters. So that's the design parameter we are talking about. M1 is fixed, that's from system. W1 is fixed, that's from our system. So if you look at this, we have this. So if you say, okay, I don't have my omega 2 equal to 0, my mu m equal to 0, and so then I just don't have a tune mass tempo there. Okay, now we simplify further, so we can look at this, and this is the equation for our design purpose. So from design purpose, you always like to use a dimensionless, because if we know the ratio of mass, we know the ratio of frequency we have, and we know the damping ratio we're supposed to get, then we can look at this as the design sense. All right. Now, what is the harmonic? This is harmonic. This U1 is our harmonic excitation. The U1, maybe say from earthquake, that come with omega frequencies. Of course, the earthquake come in, the omega can be a lot of omega in there, right? Can be many omega in there. But in Taiwan, the earthquake they're all less than 15 hertz. So above than 15 hertz, you don't worry about it, because the Taiwan earthquake in the past 100 years, they really less than 15 hertz. But how about wind? Wind is about maybe the same, less than 15 hertz, or even lower than that. So that omega is the dominant frequencies we're supposed to get. And so if we sub in this into there, then we got that. And again, from here, we'll be able to figure out what? We'll be able to figure out our transfer functions and the frequency response functions. So that's why I show you the frequency response function first, before I talk about the TMD. All right. It seems to me I run too quick, but because this is you already learned, so I'm not really. This is also the equation of motions, and for steady state solution you already learned from response, dynamic response. Just sub all those dimensionless into the system, then you got this kind of the steady state response subject to harmonic excitations and so on. And again, it's exactly the same thing. So I'm just going to run quickly, because okay. Now this is a chart I wanted you to see. Three-dimensional chart. This is my excitation frequencies. All right. And I assume M1 equal to 1. Mu M is equal to 0.01. That means my two mass is about only 10% of your system mass. Of course, that if your 101, you have the big mass, only the 86 flow. That that probably less than 1% of the total weight of the 101, right? You don't want to put too much weight in there. If you took the same weight as 101, I believe that it's going to collapse. So your tune mass, if you use the 101 as example, this 1% is also a little bit high. Maybe you less than 1%, maybe 0.1%, or even less than that. But assume this is just 1% of your system mass. And mu omega equal to 1. That means I say, well, I want to tune my TMD frequencies the same as system frequencies. That makes sense, because, of course, I want to be my tune mass tempo oscillate with my system, so that the energy will be able to transfer from my system to my tune mass system. And then that part will be able to take out the system, the energy transfer from the system, right? That makes sense. That's why we have omega like that. Then this show you, except this all fixed. I say, okay, now I have this is my damper ratio. Now, if damping ratio is too low, is close to 0, then, well, is going to oscillate, that will be no good, right? Agree? However, if you look at that, if damping ratio is about 0.3, 30%, that's no good either. So you have the gain here is very large too. And I already show you. Do you like a quicker damped or over damped or under damped? But the same happen here. Okay. So from this part, what kind of damping ratio you think you want to be? Of course, you want to be somewhere like this, there, right? Yeah, or somewhere like there. So that's being less than 10%. All right. So from this very simple frequency response functions, 3D plot, you will be able to design the damping ratio for your system. Any questions? Simple, right? EMD is really simple sense. Any questions? Of course, I assume that the 1%, my two mass sample is 1% of the system mass, and I assume that my two mass frequencies and the system frequencies are the same frequencies. Then my external frequencies is running from 0.8 to 1.2, because after 1.2 or less than 0.8, you don't worry about that anymore, because that's you don't get gain, because you don't oscillate, you don't excite the system at all. That's what it means. Okay, so we all agree now there that rho has to be less than about maybe 0.5, right? At the 0.1, 0.2, 0.3, right? 0.05 will be less than 0.05. So that means less than about 5%. I cannot be too small. Too small is no good either. So my optimum design, my best design for this system, the rho will be about 5%. Agree? Understand about this plot now? Any questions?
So I can figure out why mu and mu omega equals 1.
Okay. This is because if you like a 0.05 here, all the gain, the dB gain is, this is, for example, this is the line. All the dB gain will be smaller than any other choices. For example, if we choose this line, then that is higher than that line, right? Then that's you don't want that. In average, this line, like this line, maybe that's the best choice we can get, because this may be lower than that, and lower than this. For example, like this, we know that this is too high. That is high. This is high. This is high. This is high. So we want to have a curve that won't be this high and won't be that high. So that curve has to be somewhere between this one and maybe that one, because if too close is and this is too high, this line is too high too. Agree?
Yeah, I think he's asking about why mu omega equals to 1.
You mean why
mu omega.
This is equal to 1?
Mm-hmm.
Oh, that's just my assumption. Just I choose certain design parameter here, and I use only rho. I bet only rho is my only one design parameters. Only one. But of course you can choose a different one if you like to do that. But if I choose this design parameter of this one fixed, design parameter of this one fixed, And I have only one design parameter here I can show you. But you can change that if you like. And this is only one example. In theory, you're supposed to use all the design parameters you can use to design your system. But normally this is all fixed. In other words, your design mass, your TMD mass, you don't want to be too heavy, put on the top of 101. Agree? Your TMD mass at the top of 101, you think you want to be too heavy? No. This is why I choose 1%. 1% means my TMD mass is only 1% of the whole building of 101. That may be too heavy too.
So what would guide someone in making suggestions?
Now, if you choose your mass too small, too lightweight, then your motion has to will be large in order to take out the energy. So this is really a design parameter too. So what kind of mass you can have? I think the building designer, they will tell you that the maximum mass you can put on the 86th floor may be fixed, right? Your architectures, they might tell you, say, okay, now if you want to put a heavy items on the top of 101, the maximum weight, they might tell you that. They might give you a maximum weight for that. And that's true. So your tube mass sample cannot exceed that maximum weight. So that's fixed. And I assume that fixed like a 0.01, it's a 1%. And mu omega equal to 1, that's just only in intuition. You want your tube mass frequencies equal to your system frequencies. Why? Because that means your tube mass frequencies will oscillate with your system frequency. If you don't oscillate with your system frequencies, your system frequency energy cannot be moved to your TMD, cannot be transferred from TMD. So energy your energy comes from earthquake. Your earthquake gives the energy to your 101 building. Then your 101 building energy will give that energy to your TMD. If your TMD does not oscillate with your system, your 101, your energy cannot flow. The energy won't flow from your system to your TMD. You understand that mechanism? Why? Think about that. If these two systems, and there's no frequency involved there, and these two systems will move together. No damping. Energy is nothing. Assume your spring is very rigid, then two systems move like that. But if this system, if this TMD, if this system moving like that, and they excite this mass, so they move mass like this, right? If they move like this, that means I can have a despot there to dissipate my energy. Otherwise, it won't dissipate the energy. If this one don't have relative motions, the despot won't do anything. Can't do anything. If these two systems moving together, your energy will never be, will just keep there moving. So these two systems, TMD and building, has to have a relative motions in order that my TMD can take out the energy from your system. Just like when we walk on the bridge, right? If you match your steps oscillate with your bridge frequencies, then your bridge energy will transfer to yourself. Agree? So that's the energy transfer. The energy can only transfer to your system when your two systems oscillate together. Understand now? Any more questions? So that's why I pick up mu omega equal to 1. Purposely, I want my TMD oscillate with my system. If your TMD oscillate with the system, then your despot, because of the despot will be able to dissipate the energy out. Okay. That is the some of the comparison we have. The G11 and G21 is almost the same plots if you look at that, because they share the same denominator anyway. So that's the case here. Okay, the tension response is, I don't think we need to talk about that anymore, because you know that this is transient response. Yeah, okay. We talk about the steady state response, and then there's a transient response means this is okay now. This is mean how your two mass and your system, how they move them together. That's the transfer function. So that means your two mass displacement and your system displacement. The two mass, your system displacement, that's how it is here. That's, well, anyway, I quickly discuss about the two mass tempo. I'm moving too fast now. And that's just the simple applications. The application that I show you, all the frequent response function here. But I hope you understand. If you don't understand, ask him too. All right. Any more questions? I think we have enough today. Right? Yeah, tomorrow is holiday. And this is why we have about half the students here. But next week, Tuesday is not holiday. Next week, so we're gonna come back here. So next week, very likely, I will go to another site. So here it will become the remote site, and we'll see what happens. But I hope you all come over here, because you can ask questions too. If you want to ask questions, you can write it down and then you just type it over there, and I can see it. Or you can give to him. Okay. All right? Okay, if not, happy holiday, and see you next week. All right? Bye.